something that we're trying to do. So those of you that know Rangel, this is the experiment that they are trying to measure monopole resonance in beryllium 10 through this PN reaction. And they're using continuum. So that seems like a complicated device and certainly very expensive. So we are going to shift gears and talk about the speaker today. So Jeannie Rangel is a professor at the State University of Janeiro. It turns out we met in a talent school quite a few years ago that I led together with a few other people in reaction theory. She did her PhD with Louvain in the Universidade Federal Fluminense, also known as UF, that's what they call it. And she completed her PhD in 2017, and then she was a postdoc between Rio de Janeiro and Rangel. She did some work with Janeiro until she got her position, in which she's been working for only for a few months. It's a recent position. So I'm very happy that she's here today. We reconnected when I visited Brazil for a conference, and she's working on fusion, and in particular in fusion of light systems and light loosely bound systems, in which very often the system breaks before it fuses, and so stuff happens that only part of the system gets to be fused. So, Jeannie, I'll let you tell us about your research.
Good morning, everyone. So first of all, thanks for the invitation to talk a little about what I'm doing. So fusion reactions in collisions about nuclei with heptides. What I planned today. No, it's not working.
Click on the slides where to work. Just go to the computer.
It's not working now.
And then translate. Yeah.
Okay. So what I plan today, give some motivation, give some brief review of the theory in the years, start with classical and semiclassical model very quickly, just to figure out what is going on. Talk about the quantum mechanics model, quantum mechanical model, and our approach to do this kind of calculation. And I have to plan to show you some results involve some heavy light weakly bound nuclei. So this is a very naive illustration about fusion process during the reaction. So we have a projectile that interacts with the target, and when the projectile approaches enough to be attracted to these nuclear interaction. So they are trapped, they are bound together, and we have the nuclei compound formation. So that's a high excitation involved in the system. So after some thermalizing energy, it starts to evaporate some light particles or radiation that should be detected, and so we can get the experimental cross-section. So this is for tightly bound nuclei, so some illustrative picture. But what we have when we are dealing with weakly bound nuclei is something different. So because of this possibility to break up in the process, we have another kind of fusion, let me say, in this way. So first of all, of course, we can have that the projectile doesn't break up and is completely absorbed by the target. So we have this compound nuclei formation here, and we call this, for the theoretical point of view, we call this as a direct complete fusion because the projectile doesn't break up. But during the reaction, we can have this. In this simulation, we see a projectile that's composed by two pieces, two clusters. And so it breaks up. And then we can have that one fragment sequentially is absorbed. And then sequentially, the other one is absorbed also. So we have here the same compound nuclei that's formed, okay? But for the theoretical point of view, we call it as a sequential complete fusion. And for the experimental point of view, this cannot be separated. So they measure complete fusion only, but for the theoretically, we can split this buff contribution. I will talk about more about that. And of course, we can have that one fragment is absorbed and the other fragment leaves the region of nuclear interaction. So we have another compound nuclei formation here compared with those. So we have the incomplete fusion of fragment 1, let me say, but we can also have the absorption of the fragment 2. So the sum of this cross-section is the incomplete fusion. The sum of this cross-section here, the direct and sequential one, is the complete fusion. And the sum of all this kind of cross-section is called the total fusion. It's something that sometimes we can see in the literature. So find to this cross-section is a big challenge, not only for us as a theorist, but in the labs, it's also difficult sometimes because you have to be sure what's going on. If you have complete fusion, or you have incomplete, or you have something else going on. For example, for complete fusion, as the point of view of the experimentalists, the absorption of the beryllium 11, so to the complete fusion, the absorption of the beryllium 10 is taken into account there because the complete fusion is the absorption of all atomic number of the projectiles. So the absorption of the beryllium 11 and 10 goes the same compound nuclei with the same Z number. So for us, for sure, the absorption of beryllium 10 is the complete fusion, not complete fusion. So it's something that we have to be sure about the experimental data to compare. And most of experimenters in the past only obtain total fusion, but there are some combination of projectile targets in the literature that can be split the contributions of complete and incomplete fusion. So I will talk about some data in the last of the presentation. So about weakly bound nuclei that I studied, it involves some very low bind projectiles, but also this kind of stable nuclei, but they can be broken during the reaction. Okay, in this case, for example, for beryllium 11, this is a halo nuclei, and we have this neutron that can be leaving to the neutron can spend a lot of time away from the core, and it's the wave function gets this behavior that's long ranged. So this is a halo nuclei, and it's results some features that are very interesting. So I will talk in the end about these nuclei and those nuclei here, okay? Here we have the cluster model that we are adopting within this nuclei. And okay, speaking a little about the theory that we have, I'm starting with this classical picture because I think it's very good scenario. So we have a classical Hamiltonian to solve, and it's depend of this coordinate here, little capital 1 and R1, and is R2 that is related to the target with these both clusters. So we have interaction potential, nuclear and Coulomb, that is including the Hamiltonian, and they trace back the trajectory because they can know what's going on with this coordinate here. Okay, so the projectile here, they are bound together when this little r is lesser than the radius of the Coulomb, for example. So they know that they are bound together. So if this little r is very large, they are very far from each other. So it's featuring a breakup process. So because they know what's going on with this coordinate, when this coordinate enter in the region of either strong interaction, it can be said that we have our absorption of these fragments here. So if they are bound together, it contributes to the complete fusion, the direct complete fusion that we can see in this picture, in the top of this picture. So we have the center of mass here, and we have the movement of the deuteron and alpha particle. They are moving around the center of mass and stopping in the target. So it's a direct complete fusion. But we can also have that the fragments is moving far from each other, and even though they can be trapped in this strong interaction. So we can see that now in this moment, this movement takes some high distance, okay, you can see here, but they stopped in where the target is located. So here we have the sequential complete fusion. So both contributes to the complete fusion interaction, and we can see here the comparison with the data that we have for lesion 6 and lesion 7. So it's looking like alpha plus deuteron, and this is alpha plus triton. And we also have the contribution of from incomplete fusion. So here we can see that the deuteron is trapped and the alpha particle goes out. So the total fusion, that's the sum of all the contribution, is this line here, and the comparison with the experimental data. Of course, we can see that it's not correspond to the reality. We have some disagreements, and I just to mention that they have some stochastic consideration to the impact parameter and orientation of the projectile to the target. But okay, it's a classical picture, and I think that's very nice to see things more pretty clearly. And then we have the semi-classical model that, again, we have some, they are mixing together classical scenario because we have some concept of trajectory, but it's also using the Schrödinger equation that's time independent. So we start with the system in the ground state. We have here some probability that is changing during the time. So it starts in the ground state, and then this amplitude, let me say, for being in the ground state is diminished, and to population, the continuum starts to grow up. So because we have this probability here, they can then use this for computing fusion process using tunneling from the Coulomb value. So here we can see the results involving lesion 7 with bismuth and the comparison again with complete fusion, total fusion, complete fusion here. And we can see that there are some disagreement also. I cannot looking for another picture to see more clearly about this regime of energy. But of course, we can see that there are some disagreement with the experimental data. Something is lost. But of course, we are doing some semiclassical model, so there are something missing. For example, I know, talking with the author, that there are some conservation of energy that's violated, for example, so it's not so good. And we have this full quantum mechanical approach that take into account using coupled channel equation. Maybe most of you are familiarized with this. We have to solve some Schrödinger equation. We have this Hamiltonian here. We have to look for this scattering wave function that tell us how they are interacting. And the coupled equation concerns about we have to expand this wave function in the intrinsic wave function of our system that we are considering. For example, the target can be inert, and it will be in the CDCC model, for example, that I will talk after. And for example, we can include the projectile intrinsic degrees of freedom. And this wave function here that describes the interaction. And doing this, we put in the Hamiltonian here, do some calculation to get this coupled equation. Because to know about some channel here, we have to know about the others. So they are being solved together. The point is that when I am dealing with loosely bound nuclei that can break during the process, we don't have this kind of structure here because they populate the continuous spectrum of energy. So we have to consider some way to deal with this situation. So we have the energy of the projectile that can be very high. We have to cut at some energy. It's something like we can say that if I have a discrete projectile, bound projectile, there are some contributions of higher state that does not contribute so much, that it's little. So we can cut. Even in tightly bound nuclei, we cut here in some energy. We have a lot of L contribution because CDCC approach using that model that we have a core surrounded by a neutron or proton or a little cluster, like deuterium, for example, that we are put in a single particle consideration. So we have some shells to fill. So we have this little L here. We have a lot of that to consider and then cut at someone that's the most important. And I have to discretize these states because they belong to the continuum spectrum. So we use the Beans method. Okay, so we have a lot of pockets here and with some given energy. So it's discretized. And then we use the CDCC approach because it's coupled channel approach using this discretized consideration.
So what happens without resonance?
Well, actually, it's the same thing we do, but the discretization should be more, how to say, we have to be more carefully with there are some resonance. But yes, of course, we take it account, and you can give this information. We obtain this information because we can look for the oh my God, phase shift, for example. So we have to give some Hamiltonian to describe this projectile, and use with this Hamiltonian, we can see the resonance states. Okay, it's okay. So yes, we take into account this when it's present. So using this CDCC approach, in this Hamiltonian here, we have in the coupled channel equation, we have that the interaction potential should be complex, because we are not taking into account everything that can be going on. For example, if I deal with CDCC, I only take into account the continuum spectra of the projectile, but the target is considered to be inert, and we don't have considering some transfer process and anything else that can be going on. And so these interaction potentials should be complex, because it should absorb flux that is not taken into account directly in the approach. So it has to be complex, and the imaginary part of this optical potential takes account to the loss of flux. And in case that we considering this interaction as some interaction that acts inside the Coulomb barrier, we are taking account for fusion only. It's not takes a long range that we can afford to indirectly account for inelastic reaction and so on. So if this one is this kind of ion interaction, we are considering only the absorption to fusion. Okay, so CDCC actually they use it. We have to use the interaction potential that contains the dependence of this coordinate and this coordinate. Okay, but in this approach from Rangel, Vittori, Nancy, they used this interaction here that depends only by this capital R. So what they are telling us is that the absorption of the center of mass is considered to the fusion. So the components that belongs to bound state goes to complete fusion, and we can split of the components of the continuum spectra. They are broken, so the absorption here goes to the incomplete fusion. But they didn't go too further because they have some issues, and maybe we can try to trace back this issue looking for a classical picture. So here we have that bound state contributes to complete fusion and continue to goes to incomplete. So the sum we have the total fusion, for example. They have some limitation because it works something good for when the fragments here, one of them is much heavier than the other. So in that case, because the absorption, the center of the mass is taken into account, we can see that the absorption when they are bound together, okay, we are looking in the process that whole projectile is trapped. But when we are in the breakup space, maybe, okay, the absorption of the center of mass maybe can be taken into account the incomplete fusion, for incomplete fusion. But when the fragments have such a comparable mass, so maybe this kind of interaction is not so good because maybe they are very far apart and we are downstrapped any kind of fragment. So maybe they are overestimating the incomplete fusion. So we think, what about using this interaction? Because we have to deal with it with CDCC calculation. So we use this interaction potential here to describe the fusion process. So we have to put there some information of intrinsic degrees of freedom of the projectile and so on. we can split this equation in a simple, we can mix something, comprise some information together and look to this equation as a sum of two probabilities. The probability to absorption, the one fragment and another fragment here. So just to be quickly to show you the information, not take too much time here. We have this probability that take into account with this information. We have a lot of information here of the intrinsic for the intrinsic states of the beams and so on, information about the relative movement of the projectile target, and and the form factor here about the interaction that we have. So just to show that's a huge equation, but it can be summarized this way, okay? So I have split this contribution. So in the first place, we have the contribution from the bound state. So here we have only, actually, sorry, we have to consider prime here in this wave function. And I realized only just a few minutes to get in. And so, because sometimes we can have more than one bound state. And the contribution of the bound state we have goes to direct complete fusion, okay? So they are bound together, this is the scenario. But we are not considering this because we just found out that the absorption using this is very high. So only for bound states, we consider that kind of assumption, like this approach, that we have a potential that depends only by this capital R, okay? Only for bound state. So they are bound together, we change this potential for that, and we have the absorption of the center of mass, and okay, this go for direct complete fusion. But to consider the continuum spectra, yes, we are doing this calculation here, and we have this contribution. But this tells us nothing about incomplete fusion or sequential fusion, because we are only saying that some particles are being absorbed. So we have to enter in with some model using these probabilities. And what we have done was to consider the incomplete fusion. We take this probability of fusion of fragment 1 multiplied by the not probability of the fragment 2. And the same for the fragment 2, okay? Change it here. So we are dealing with this process here. And for sequential complete fusion, we have only multiplied both probabilities. So they belong to continuum, and we have this multiplication. So with this cross section, we summed with the direct complete fusion they are bound together. We have complete fusion interaction, cross section, sorry, and here we have the incomplete fusion, okay? So just to summarize what I actually do to obtain my cross section. This CDCC method is taken into account using Fresco code. And then we know that it is looking for the wave function, the behavior of the wave function asymptotically to get this information and extract the last cross section and breakup cross section and so on. But I do CDCC calculation using Fresco to extract the scattering wave function, okay, for some a lot of angular moment, but I'm interested in this region here that's inner through the barrier to estimate my probabilities, because I have to do this calculation here in principle, yes. So here we have this scattering wave function, And so I have to extract it from Fresco and do this calculation in another code to separate this contribution. Okay, that's what I'm doing. So now I am show you some results about all of this I talked about. So first of all, I have this system, considering the little 7 that I said, it's a cluster of, it can be seen as a cluster of alpha plus triton that's loosely bound about 2 and 0.50 MeV, something like that. And here we can see the comparison with total fusion cross-section and complete fusion experimental data. And we can see some good agreement with the complete cross-section, okay? But total fusion is something that we are overestimate. But we have some explanation about that, because when the projectile breaks up and each fragment is absorbed by the target, we have this compound formation here, as actinium and polonium, and they start to evaporate. And the last actinium in this chain, we have a process here, the beta decay, sorry, and it goes to polonium chain that belongs in the first moment to this absorption here. So in principle, they cannot split in the experiment both contributions. So we have incomplete fusion only, not information of incomplete fusion 1 or 2, okay? Only incomplete fusion. And for this polonium here, they have a long half time living. So they cannot detect it. All cross-section belongs to this incomplete fusion because they cannot, of course, wait to have this decay here. Okay, so they look for the basic code to estimate the contribution of this compound nuclei here, and they found that it's very important for energy that's higher than something like 36 MeV. So when I put this picture again, but only for incomplete fusion, this data here is something that they are be sure that we have all channels of this evaporation contribution to the complete fusion, but this is something like the lower estimation because we cannot have the contribution doing by this polonium here. Okay, so when we compare with considering that, when we compare, we can see that we have agreement in the energy regime. They have sure that it's good, and we are, of course, overestimate this lower limit. Okay, but it's something that is in agreement with the experiment. So it's consistent. And we have this all cross-section also for complete fusion with this, all these targets here, gold, tin, and platinum. And we have also a good agreement only, you have to look to the solid black line here to compare with the cross-section. Okay, here we have a kind of oscillation of the data, but we can see a good agreement with the experimental data. And for the complete fusion, is something intriguing that we can describe the absorption of the triton at all targets here, but not describe the alpha absorption. So for us, it's very intriguing because in the same calculation, we are only splitting the contribution, okay? And we have a good agreement with the complete fusion, the incomplete fusion with the triton, but not the absorption of the alpha particles. So it's something that we are not understanding what's going on in this moment. Maybe, I don't know, there are a little problem with the acquirement of the data. We don't have too much say about that in this moment. And now I'll talk a little about complete fusion involving neutron valence particle nuclei. For example, I said in the beginning of the presentation, the beryllium 11 is composed by beryllium 10 plus neutron. In this situation, we have to be sure about the data if they are considering that complete fusion is only the absorption of the beryllium 11 or even the contribution of beryllium 10. In this case, for this system, they said that they have both contribution to the experimental data. So unfortunately, the data is very broad, here. So we can say that we are in agreement in the sense that the data, we can describe the data in the lower limit, but it's very, I don't know if it's not oscillation, but it's very broad, so we cannot say too much. But we can see that we pass through some experimental data here. So we are considering our approach the sum of complete fusion and the absorption of the core, okay? And in the paper of the experimental data, they said that the contribution of the absorption of the core is something less than 30% of the complete fusion. So because we can split the contribution, we can look for this information. And we have split it here, complete and incomplete fusion of the core. And we can see that, yes, the contribution of the absorption of beryllium 10 is something nearer of to 80%. So it's less than this. So it's quite in agreement with they said in the paper here of the experimental data. For helium-6, I have to say that we are doing some considerations because in principle, helium-6 is a cluster of alpha particle plus 2 neutron. So it's a 3-body problem, but our approach is considering only 2-body projectile. So what we have done was, I didn't put here, I think, the information, sorry. We looking for our work made by Antonio Guro, that they reproduce the elastic cross section of helium-6 with some target that I can remember right now. They compared both calculation using this 3-body projectile and consider 2-body projectile. So they look for this kind of system and find out that to use it 2-body problem, the dineutron has to be more bound to the core. So we get this information using this binding energy to run our code to consider the same wave behavior of the wave function of the ground state. So using this, we done our calculation to this system. And in this experiment, they said that the experimental data is complete fusion, not taking into account the absorption of the alpha particle. So we are comparing only complete fusion cross-section, not the incomplete fusion one. And you can see a very good agreement with the experimental data. And for helium plus, thank you. we have again some agreement. We can see some kind of different behavior here from the cross section. Our result is that the inclination of the curve change, but we can also see some things happen with the data here, but we can see the agreement with the experimental data. Okay. So in conclusion, we have proposed this quantum mechanical method to evaluate complete and incomplete fusion, and incomplete fusion in collisions with weakly bound nuclei. And the method was applied for lithium-7 neutron, actually for lithium-6 also, but I didn't show because it's a lot of information. And we have compared the cross-section with good agreement to all systems. And all the calculation is going on with some light system. But here the problem is that the cross-section we have in the literature sometimes we don't have too much information about if it's total fusion or complete fusion, or if they are estimating incomplete fusion, or they have measured the incomplete fusion, something like that. So it's something that's very hard to do in this moment, but we are trying to do calculation for some experimental data. That's the people that I work with this problem of fusion. And as Filomena said, I still working with Jesus Lubian Rios from this university here that we call UF. And Vinicius Zagato, I don't know if you know this professor. From the university from Rio de Janeiro, we have this both university that's federal, I don't know how to translate. And we have the professor Luis Felipe Canto, maybe you know him. I started this collaboration with Filomena here. It's a pleasure for me to start this collaboration. And we have two, actually, they are postdoc. I put wrong. Marianne and Jonas, I don't know if you know, they people, but the people that I'm working with this problem of complete and incomplete cross-section. So that's it.
Question from the audience?
You.
Okay. There's I noticed, yeah, the last slide, there's no error bars in your calculation. Is there some opportunities for quantification or?
Sorry, this one?
Yeah.
Yeah, sorry, can you repeat?
So there aren't any error bars in your calculation. Are you gonna look into it?
No. Our calculation does not consider this.
Okay.
This.
Do you plan to address that?
Yeah.
I don't know. I never thought about that. Yeah, I know that you here are doing this kind of calculation. It's interesting. Maybe you can share information or something else because it's something good. But no, we don't use this kind of information.
Before you leave, I will be more than happy to have a chat about that.
Yes, of course. Actually, I saw your presentation this weekend. Yeah.
But yes, let's talk about it.
Okay, good.
But perhaps a follow-up question that's related. Do you want to say a little bit about the parameters? Because of course your Hamiltonian has parameters. And the interactions have to be parameterized in some way. So if you want to say something about that.
I could use the Hamiltonian here. You're using, in principle, the nuclear interaction, the real part. We are using, I don't know if anyone here knows this interaction, but we are using the São Paulo interaction potential. So this is a kind of a double fold interaction. that's something microscope. So for the nuclear part, we are dealing with this interaction potential. And for this interaction here, is something, or also that, is something like a Wood-Saxon shape, okay? Because it's, I don't have any picture here, okay? It's something like, it's,
I think they know what looks like.
okay, so, okay, it's a Wood-Saxon shape with some parameter that is hardly used in the literature that's considered to fusion process. I mean, again, the main subject here is to understand that we are simulated the Depletion flux, sorry, that when it passes through the Coulomb barrier, it's trapped. The flux does not leave out. So it's something like Rangel wave boundary condition, and we have this shape. So to represent fusion process is to represent, because actually fusion is not a channel that can be put there as information in the CDCC approach or CC approach, or even for transfer process when using this kind of optical mode interaction using Fresco code. Okay.
Any more questions?
No, I think it's not. Okay.
So I have questions. So about these CDCCs, I think there was a question about resonances, and I guess when you get to the region of resonance, in the energy region that is close to resonances, you have to have very fine.
Yes,
tuning.
yes. We have to discretize more.
Okay, so this discretization by itself give you some kind of concept of resolutions in your wave, in your basis. Energy resolution.
Yeah, I don't. Let me see. What we do is, yes, we can see here this pocket that's very broad. Yes, if you have some resonance here, it's have to be more. We have to. I had to say, my God. More discretized, so we have more wave function, more pockets here. Okay, we have more test script, and we can look for the phase shift and compare information about something like the position of the energy and the width, because we can see the phase shift and put something like sino squared and observe the width. Oh my God, we have a peak, we have the higher half.
Yes, I understand.
I forgot the name, sorry. And we can compare this information with some information we have in the literature about this structure.
Yeah, I think my question is more conceptual. Is when this basis, right, phi wave functions, are they real asymptotic, like oscillating to infinity, or actually they are localized?
No, they are asymptotically oscillating. Yes.
But they have some finite energy resolution for the basis.
Yeah, I don't know exactly how to what to say about that. I don't know exactly.
So I'm naive. I was thinking if you have some finite energy resolutions, it's actually a wave packet. So it's a finite.
It's all wave packets.
It's a space.
Yes, it's all wave packets.
Even if they're not a resonance.
Yes,
they're
it's all.
transforming everything into wave.
Yeah, but in the coordinate space, they are really like a finite object. They are really not like sine or cosine wave function.
The amplitude outside is very small.
Okay.
Yes, but still oscillating.
For a resonance, it's very localized. And actually, we capture the resonance in one bit.
But I think in
Yes.
these bases, all the bases you're having, they are all separately localized because you have finite energy resolution.
Correct. And and she checks convergence. to
Yes,
that.
yes, I have to check. It's some hard task to do CDCC calculation.
Okay, we don't have more questions, okay. Thanks, Peter.
Shalene, I have a question. I don't know if I can ask.
Slowly,
Oh, okay, please go ahead.
slowly.
Hi, very nice talk. So I have a, so when you're doing this CDCC calculation at this very low energy near the Coulomb barrier, how many partial waves do you need to include?
Actually, it's a good question because to do fusion, because we can only, we are looking for the fusion process. We are not treating at high angular momentum. So we cut in 60 or something like that, because we can see that the fusion process is going smaller and smaller when the energy is lower. So
I guess, I'm talking about the partial wave between your core and your fragment, not the projectile target.
okay, sorry. Yeah, actually we are not using too much, something like it's in this slide right now. So L equal
Okay.
2 or something like that. It depends of the projectile we are dealing.
And it converges quickly? I mean, this,
For low energy, it's not so fast, and it's terrible things to deal with, to the convergence of the energy that's below the Coulomb barrier. It's hard to obtain. Sometimes I change it to R matrix formulation in fresco to get more stability.
And up to which energy in the core fragment continuum do you have to go?
It's sometimes something like 8. I can remember the information for lithium, okay, but I think it's something like 8 MeV.
Okay, right.
And for
Okay.
helium, I think it's 6 or something like 6 or 8. I think
Okay.
it's 8 below, and no, sorry, 6 below and 8 above the Coulomb barrier we are using.
Okay, thank you.
Welcome.
People are quiet, no questions. Thanks, Peter. Oh, yeah, by the way, do you want to say about her schedules?
Oh, yes, Jeannie is here until Friday. I know